Hey everybody, and welcome back. All right, we have finished Unit 1. We are going to start Unit 2 today. And Unit 2 is going to be all about linear and nonlinear functions. Basically, the unit's called functions. Today, we're going to be talking about relations. So what is it? How do they work? We're going to particularly be focusing on graphs today. And then we're also going to bring up these two words, domain and range. Our essential questions for today: what is a relation? What are domain and range? And then what's the difference between continuous and discrete? So if I throw out those words like this is a continuous graph or this is a discrete graph, like what does that mean? All right, let's kick it off with relations. So relation, when we're looking at two different things and they're changing in response to one another, we say, okay, there's a relationship there. When we graph it, it's a relation. So relationship, there's something linking two variables, and then when one changes in response to the other, we have a relation. So like some things you might see on a daily basis, like your location in the school is related to the time of the day. So at a particular time of the day, you should be able to tell roughly what location you should be in the school. If you're earning money from a part-time job, particularly if you're paid a wage, so you have an hourly wage, you can tell roughly how much money you're going to make based on how much time you work. Driving the car, you can tell how long it would take you because you know that there's a relationship between speed and distance, and then the time that it would take as well. So if we can describe a rule that would link the two of them, that basically shows you how one changes in response to the other, we can say we have a relation equation. All right, domain and range are two new words that we're going to talk about, and they're words that you really need to know what they mean because questions are going to just very straightforward ask you what is the domain and range of the graph. And if you don't know what those words mean, you're going to find it very difficult to make any sort of stab at answering the question. So highly recommend you take this page, this particular slide, write it down word for word, make some posters, make some flashcards for yourself, whatever it takes, because you need to really focus on learning your vocabulary here. All right, so domain is the input of a function or a relation. So it's what goes in. So when we say what goes in, we're talking about like if you have two variables or two things that are dependent upon one another, one usually changes in response to the other. The domain is the independent one. This is the one that you change. So this is what goes in, and then the dependent, which is the other word we're going to talk about in a second, is what changes in response to it. When we're looking at this on a graph, it is typically the x values on a coordinate plane. So it's the x-axis would show you our domain values, and then the x-coordinates would be part of the domain. So independent variable. And then the other one is the range. So the range is the output of a function. So it's what comes out. The y values on a coordinate plane, and this is known as the dependent variable. So this is the one that will change in response to the other. So like if we were talking about that example of you in school, we would say your location in the school is dependent upon what time of the day it is. So at 7 a.m. you're in your first block, or you're going to your first block class, you're coming into school. At 9:30 a.m. you're in your second block, so you're having math class with me, and so on. So the time would dictate where in the building you are going to be. So location is the range, time is the domain. So this is one that it's probably going to take you a little bit of time to just kind of get used to, okay, what do these words mean? They're not words that I would typically use in English everyday language, so it's not something I have much experience with. And you're going to have to start identifying this over and over and over again. And even like all the way up through Algebra 2, any higher levels of math you would do there, you will continue to use these words, domain and range. So allow yourself some time to get used to them. So if we're looking at a graph like this, this could be, it reminds me of like a money graph, like a savings graph. So you would say like, I'm putting money into savings, I'm investing it, so it's growing with an interest rate. So domain in this case would be time. So as time passes, the amount of money you have would increase. So time is the domain, amount of money you have is the range. So as time progresses, the amount of money you have starts to grow because exponential growth is taking over. So like just speaking of money, here's a real life example of this. So you have money invested in stocks or something like that, and here's the value of your money over time. So you can see domain value is time, and then the range is the amount of money that you have. So when you're investing in something like stocks, you can expect your money to go up, down, do a lot of different things, but over a longer stretch of time, it is growing, and it's growing exponentially. So a relation, we've already talked about this, is just a relationship between two given values. We're usually going to put it in the form of x, y, so we're going to try and take those two values, represent them mathematically, so we'll use equations to solve for each one, but we'll also represent them on graphs, and we use the coordinate plane, so an x-y axis, to represent those. So our x value is the domain, our y value is the range. So ordered pairs is what we call the different coordinates that show this relationship. So an ordered pair has an x value domain and then the y value that would go with it. So like I said to you, at 10 a.m., you know that you are in math class, so 10 a.m. would be the x value, math class would be the y. Okay, so just looking at graphs, especially with relations and functions, there's going to be two different types. There's going to be discrete and continuous graphs. The one on the left is a continuous graph. The one on the right is a discrete graph. So a continuous graph is basically one where you don't ever have to lift your pencil off the page to trace your hand along it or to draw it. So like I can start at the beginning, go up, over, and I never have to lift my pencil off the page to do this graph. A discrete one on the other hand, there's breaks. So you can't go from the first dot to the second without lifting your pen off the page. So discrete, you lift your pencil off the page, continuous, you do not. And discrete would tell you that there are values, so there's parts of the domain that do not have a relation, or same thing with the range. Versus continuous, no matter what moment in time I pick, there's going to be a distance that I've traveled. Like I can't just skip over some period in time and be like, oh, actually at this time I totally disappeared, so I didn't travel any distance at all. So things like time are continuous. Things like number of units that you buy or things that you do, so there's like a whole number set of units, that one would be a discrete function or a discrete relation. Okay, so looking at this one. This one is a continuous relation because remember you can trace your pen over that entire thing without having to lift your pen off the page. This one shows the distance a delivery van is from the warehouse as it varies throughout the day. So the graph shows the distance from the warehouse for a day from 8 a.m. to 5 p.m. So delivery van goes out, leaves the warehouse, goes to looks like 9 different stops or 9 different points where it does something, and then comes back to the warehouse again. So like in both of these cases, like it's back at the warehouse because that's the distance from the warehouse. So when it hits the line, that means that the distance is 0, it means it's back at the warehouse. And then we've got time. We went from 8 a.m. to 5 p.m. So our domain in this case is the input, that is the time. So time is the domain, and then distance is the range. So the y values are the range. So like we might say, at this given moment in time, we are this far away from the warehouse. Okay, segment number 1 shows the delivery van moved away from the warehouse. Okay, get that, started at 0, 0, so it started at 0 distance from the warehouse at time 0 and moves away. What does segment 2 show? So now you'd have to think about, what does the steepness of the lines mean? So as it has a steeper slope, so that slope refers to the rise, so how up, down it's going over the run, right, left. So the steeper it is, the bigger the rise is, and the smaller the run. So the distance horizontal that it travels is dependent on how high it goes as well. So like the difference between 1 and 2, in 1, it traveled a greater distance in a shorter period of time. In 2, it traveled a smaller distance, so the vertical part is smaller, it looked like maybe a similar amount of time. So we would say segment number 2 shows that the van was moving, so it got to this point, it had a steady speed for that first hour, we'll call it, or whatever unit of time that is, but then it had to slow down. So it was covering less distance in the same amount of time, which means that its speed has dropped. So we might say like, okay, the first part, it was on a highway, so it's just getting out of the warehouse. Second part, it's into a town or a city. And we're dealing with a lot of traffic lights. We're having to drive at a slower speed limit. It's going slower. So segment 2 would say it's going slower. Based on the time frame, what change in the distance from the warehouse is represented by segment 6? So segment 6 is the first time that we see a negative slope, so that when we read it from left to right, the distance is actually going down. It's the first time. Up until now, from left to right, the distance has been increasing. Segment 6 is the first time it starts decreasing. So this is the point at which the van starts to head back towards the warehouse. So it might be like, if you imagine a road map, it might have a route that takes it far away from the warehouse, hits some stops along the way, and then it starts coming back and hits different stops on the way back. Which line segment shows the intervals where the distance did not change, and what is a possible explanation for these? So no change in distance are the flat ones. So that's 3 and 5. So the distance didn't increase, but the time did. So the van was sitting still. Possible reasons that a delivery van is sitting still: it's making a delivery. So it's pulled up outside of a store, restaurant, school, whatever it is, and it's unloading its cargo. So it's taking some time to unload the cargo. It could be at an accident. So it's come across an accident, stuck in traffic, can't move. It's hitting long traffic lights, whatever it is. We don't know. So whatever the reason is, the van is stopped, and you can give some possible explanations for it. The driver may have had to go to the bathroom, so it pulled in at a gas station, or it's filling up on gas, that sort of thing. All right, we got 3 graphs here, A, B, and C. And they all have slightly different shapes, but they all have a domain of time and a range of water in gallons. Okay, so 3 hoses fill 3 different water barrels. A green hose fills a barrel at a constant rate. A black hose is slowly opened when filling the barrel, and a blue hose is completely open at the beginning and then slowly closed. The 3 graphs of the situations are shown. So then which graph represents each hose? So we've got 3 hoses, a black, a green, and a blue. The green hose fills the water barrel at a constant rate. So that means you turn the hose on, you leave it on at that rate for the entire time. So as time passes, the amount of water in the barrel should be increasing at a steady rate. So that is this one. This is the green hose. A black hose is open slowly when filling the barrel. So in the beginning, it's going to be quite small because it's barely open, and then it's going to open faster and then let more water in faster, faster, faster. So that is this one. So the amount of water in the barrel is going to start quite slow. It's going to increase, but at a slow rate. And then as the hose opens up, it really starts to fly up and fill the barrel. And then like gets to the top, the barrel's full. So at the top of each of these, the barrel is full. Which means that the last one must be my blue hose. And this one, it starts fully on, and then we kind of close it off as we go. So the amount of water in the barrel increases very sharply in the beginning, but then it starts to slow down. So the slope gets a little bit less as the time progresses, but it still fills the barrel. All right, sketch a graph to show your percentage score in class compared to the letter grade you receive on a report card. Okay, so that would mean that we have to think about what's our domain, what's our range. So does the letter grade you have on a report card dictate your percentage grade in class? It can tell you something about it, but it wouldn't dictate it. The other way though, the percentage you have in class dictating the letter grade, yes, that is totally true. Especially when report cards are something that would come out on a regular basis. This should be a very relevant thing for you. So on the bottom is our percentage grade, that's our domain. And we'll assume that there's no extra credit or anything like that involved. Your percentage grade would range from a 0 to a 100. So like halfway in there would be a 50, 60, I'm just like roughly making these up, 70, 80, 90, and 100. And then lower again, 40, 30, 20, 10. Letter grades, lowest one would be an F. E, oh, there's no E technically, so I'm just going to delete that one. D, C, B, and A. So what we know is that if you have a 0 to a 59.9%, you are considered to have an F. So what we would say is at 60, you go up to a D, so this one is not included. So remember our inequalities notation, this gets an open circle. And we would have a horizontal line. Now, if I could draw a straight line, that'd be great. But a horizontal line that would say from 0 to 60, but not included. So anything less than 60, you would have a grade of an F. If you score between a 60 and a 70, but not including 70, you would have a D. So 70 would get an open circle. If you score between a 70 and an 80, but not including 80, you would have a C. If you score between an 80 and a 90, but not including 90, you would have a B. And then if you score anywhere from 90 to 100, you would have an A. So this is what we call a step graph. And this is a discrete graph. So we had to lift our pen off the page to draw this graph. So a step just refers to the style that, you know, every number in the domain is accounted for, but then there's just like jumps in the range. So the range is not fully accounted for. So like A, B, C, D, F are separate categories. There's no like continuous rate in there. Versus if it was GPA, it might be slightly different. There would be a continuous line for that. So you're going to be asked to draw some graphs too. So you'll get a scenario and you'll be asked to draw a graph, and you might have to do a discrete one or a continuous graph, depending on the scenario. All right, you're going out to the post office to buy stamps. You're only able to buy them in quantities of 5. So you go to a post office, you say like, I want a single stamp. Sometimes they're like, no, we sell them in books of 5. And stamps cost 52 cents per stamp. Excuse the typo there. So that'd be $2.60 for 5. So we're going to create a graph showing the number of stamps we can purchase and the total cost for purchasing them. So number of stamps, you know, we're going up in 5, so I'm not going to do ones. So let's do 5, 10, 15, 20, 25, 30, 35. Stamps is the domain, so the more stamps you buy, the more the costs increase. Now you could make the argument that the higher the cost, the more stamps you have bought. Probably true, but I mean the cost could also include other things, so it's sometimes reversible, sometimes not. In this case, we were told stamps is the domain, total cost is the range. So if we buy 5 stamps, it's going to cost us $2.60. because it's 52 cents per stamp, $2.60 for a book of 5. We can't buy 6, we can't buy 7, we can't buy 8, we have to buy 10 next, and that would put us at $5.20. 15 will put us at $7.80. 20 will put us at $9.10.40. 25, and so on. Like, you guys get the idea. It would look like this. So this is what we would call a discrete graph. Again, so discrete. Another characteristic of this one is that all the dots are in a straight line. So we will call this a discrete linear graph. So if the dots or data or continuous line is straight and there's no other curves in it, no twists, turns, turning points, it's called a linear graph. So we have been doing some linear equations in Unit 1. When we start putting them on graphs, you'll see like, oh, these actually produce straight lines. All right, your turn. Sketch a graph of the two situations and tell me the domain and range. So put some labels on the graph. Domain should go on the x-axis, range should go on the y. So at the start of a snowstorm, it snowed 2 inches an hour for about 2 hours and then slowed down to 1 inch an hour for an additional hour before stopping. 3 hours after the snow stopped, it began to melt at 1/2 an inch an hour for 2 hours. So you're going to have to graph that one. Second one, a local salesman is going door to door trying to sell vacuums. For every vacuum he sells, he makes $20. He can sell a maximum of 10 vacuums a day. So we're going to graph both of those scenarios. Pause the video, come back when you're ready. Okay, so start of snowstorm, moved 2 inches an hour, or snowed 2 inches an hour for the first 2 hours. So at the start of a snowstorm, we've got time, and then we've got inches of snow. So start of a snowstorm, we're at time 0, inches of snow should be 0. 2 inches an hour for 2 hours. So we got 1 hour, 2 hour, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. So for the first 2 hours, it snowed 2 inches an hour. So the first hour would have 2 inches, the second hour would have 4. And then it slowed to 1 inch an hour for an additional hour. So hour 3 only went up 1. And then for hour 4 stopping. So it stopped snowing, so it would stay flat. And then 3 hours after it stopped, 1, 2, 3, it started melting at 1/2 inch an hour for 2 hours. 1, 2. So at 1/2 inch per hour, that means in 2 hours, it would melt 1 inch. So go back down 1. All right, now this one, the snow doesn't just come on the hour. It's been falling continuously. It's been accumulating. It's been melting. So this one would actually get straight lines between them. And we would consider this to be a continuous graph. So you should be able to draw it without having to lift your pen off the page, kind of thing. Like, it all connects. So domain time, inches of snow, range. Make sure you're doing this with a ruler, by the way. I don't have a ruler tool on my trackpad, though. Actually, I wonder what happens if I put a ruler on it. Not super easy to like get the point right where I need to be, but yeah, it's not bad. Okay, second one. Vacuum salesman going door to door, selling vacuums. For every vacuum he sells, so for every vacuum. So the vacuum selling is the domain, and then the money is the range. So money is the range, and then vacuum sales is the domain. And you can sell a max of 10. Lowest will be 0. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If he sells one vacuum, he makes 20. So 60, 80, 100, 110, 120, 140, 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. All right. So if he sells one vacuum, he makes 20 bucks. If he sells, you can't sell half a vacuum. It's not possible. So we can't make $10. So this is going to be a dot. 2 vacuums, $40. 3 vacuums, 60. 4 vacuums, 80. 5 vacuums, 100. 120, 140, 160, 180, and 200. So this is a discrete linear function or relation. So the first one was nonlinear because it kind of went off all over the place. It was not even a curve, it was straight lines that ended up not being all continuously linear. And then the other one was a discrete linear function. So this one is a continuous nonlinear function. All right, so your job is going to be textbook page 91 to 94, questions 1 through 17. You can find the digital link for that on Schoology, or you can use the textbook in class. Our essential questions for today: what is a relation? A relation is when you have two random terms, things that have a relationship and that one changes in response to the other. Domain and range. Domain are the inputs, the x values, the independent variable, so the one that you can change, and then the range is the output or the y coordinates, and this is the one that changes in response to what the domain does. What is the difference between continuous and discrete? Continuous, you can draw the graph without lifting your pen off the page. Discrete is separate dots or line segments, so it's not something you can draw without lifting your pencil off the page. And then for tonight, textbook pages, make sure you finish it, questions 1 through 17. All right, I'll see you for next class.